Hello, can you hear me?
Yes, ma'am.
Okay, and my screen is visible?
Yes.
Okay.
Ma'am, full screen mode, full screen.
Yeah, yes. Yeah, so first of all, thank you very much for inviting me in this particular FDP. And thanks to Dr. Sabbasachi, who was in touch with me for a long time. And thanks for the invitation. And today I will talk on these dialogue systems. So basically, dialogue systems are a very recent application areas of AIML, artificial intelligence and machine learning. So I will discuss how machine learning algorithms can be used to develop the dialogue system. So basically, what do you mean by dialogue systems? Like you are already aware of this Alexa or Siri. Like this Alexa is basically a dialogue system, so you can chat with Alexa can use as a question answering system. You can ask for the weather forecast, or you can ask for any other questions, or the for songs recommendation, etc. So to Alexa. So how can we build a Alexa like system? So that is basically called a dialogue system. So this is the overview of my talk. So I will firstly discuss what is the definition of a dialogue, then what is a dialogue system. Then the dialogue system has many components. We will soon show you the block, the chart, basically the flow of the dialogue system. So dialogue system is having one component called the Dialog Act Classification, then the intent detection and the slot filling, a dialogue manager. So we will discuss about this sub modules of dialog systems, and then there is we will show you how sentiment we can make the dialogues more sentiment aware. So when the virtual agent is talking to a customer, the virtual agent should also be sentiment aware. Like the virtual agent should not say anything to the customer which will make the customer unhappy. So how can we use the sentiment and emotion to make the virtual agent a realistic agent? So these are basically the overview of my talk. So let me start with the what we mean by a dialogue. So it is basically conversation with a agent, or agent could be a kind of a robot only. It is a chat bot. So it is a chat robot. So now customer has to chat with the chat robot. So like suppose the chat bot is asking, "Hello, how can I help you?" So the customer is saying, "My computer isn't working." So then what is it is a task oriented chatbot. So the task of the chatbot is to somehow solve the problem of the customer. So customer is facing a particular problem, and the chatbot will try to gather information, and then it will search in the database. So already it is having a database where the solutions of several problems are already listed. So it will try to get enough information from the customer, and then it will try to search with those information in the database, and then we'll give the solution to the customer, and so that the customer just to make the customer happy. So there will be several utterances, like several utterances of the agent and the customer, and then finally that maybe the agent is able to solve the problem, so the customer is very happy, great, that solved my problem. So this is called the task oriented virtual agent. So basically there is a particular task of the customer, and the virtual agent has to somehow solve the particular task by gathering information from the customer, and then by doing a database search. So what is the definition of a dialogue? So dialogue is a formal discussion of a topic in speech or writing. So it is a connected series of utterances, a text or conversation. Okay, so dialogue is a formal discussion of a topic in speech or writing. It is a connected series of utterances, a text or conversation. So exchange of ideas or opinions on a particular issue with a view to reaching an amicable agreement. So it is an exchange of ideas or opinions on a particular issue with a view to reaching an amicable agreement. So there are several characteristics of a dialogue, like whose turn is it? Like whether now the VA has to say something or the customer will say. So whose turn is it? Then what are the intentions? So when the user is asking something, what is the intention behind that particular utterance. So maybe the user wants to book a flight ticket, or maybe the user is interested in booking a restaurant. So the user intention has to be understood by the virtual agent. So what are the intentions of a particular user? And then how to reply back. So once the intention is known, how the virtual agent can reply back. So these are the characteristics of dialogues. So this is the overall block diagram of a dialogue system. So suppose the user is asking which restaurant can I book for 2 people for today. This is the user input. So then there is a natural language understanding module. So the natural language understanding module will try to analyze the user input. It will try to extract the important information from the user input. So basically there is this Dialog Act Classification. So Dialog Act Classification determines the communicative intention of the user. So in this case, it is a question. So there are different communicative intentions. Like it could be a greeting, it could be a statement, it could be a question. So the Dialog Act Classification basically tries to identify the communicative intention of the user. So in this case, it is a question. And then there is an intent classification module. So the intent classification module will try to understand the intent of the user. So here the intent is booking a restaurant. And once the intent is known and the Dialog Act is all known, there will be a slot filling module. So the slot filling module will try to extract information from this particular utterance. Like which restaurant can I book for 2 people for today? Here the important slots are 2 people and today. Okay. So 2 people and today are the important slots, and those have to be extracted from the particular user utterance. So that gives us a state representation. So the state representation is the date equal to today and number of people equal to 2. And it's basically, it's a question. So basically, that is the state representation. So state is basically, it is asking to book a restaurant for today and with number of people equal to 2. And then there is a dialogue management component. So this dialogue management component is nothing but the reinforcement learning based agent. So this basically maps the state into an action. Okay. So basically, given the state, it basically selects the appropriate action for the virtual agent. So given this input, the virtual agent has to select an action, and that mapping is basically done by the dialogue manager. And finally, this action is translated into the system response by the natural language generation module. So there is an action, and this action is translated into system response by the natural language generation module. So this is the overall diagram or block diagram of the dialogue system. So dialogue system is having a natural language understanding module. So here there are mainly 3 sub-modules: Dialog Act Classification, Intent Classification, and the slot filling. And then there is this natural language generation module, which is translating the action into the system response. So now we will discuss about the Dialog Act Classification. So Dialog Act Classification is the first submodule. So Dialog Act Classification aims to identify the communicative intention of a speaker in a dialogue conversation. So like whether the speaker is asking a question, or he is simply expressing a greeting, or it is a statement, or it is an understanding. So all these are different dialogue acts. Like what kind of experience do you have with the child care? So this is a question. I think it is really, this is a statement. How about you? This is an open question. That's all right. This is the understanding. So basically, these are the different dialogue acts. So in this case, the data set is that we have used is the HWBD. This is the switchboard corpus. So this is an informal corpus of human-human interactions. So here there are 1,155 number of dialogue conversations amounting to more than 2 lakh utterances. So this tag set is comprising of 1242 categories of dialogue acts. Okay. So HWBD DAMSL tag set is comprising of 42 categories of dialogue acts. And basically, and then there is another data set which is called the trends data set. So it is a task-oriented corpus where a user collaborates with a planning assistant to accomplish some task involving manufacturing and shipping goods in a railway freight system. So there are 98 dialogues amounting to more than 7,000 utterances. So these are the two popularly used dataset, SWBD and the trends. So we have basically used some machine learning and the deep learning based approaches for solving this Dialog Act classification task. Okay, so you can understand this is a classification task. So given a particular utterance, it is a sentence level classification. So a sentence would be given to you, the user utterance would be given to you, and you have to basically classify this in any of these 42 categories. So basically we have used some machine learning and the deep learning based techniques for solving this Dialog Act classification problem. So what is the motivation? So first of all, we have developed a taxonomy. So these 42 tags are not frequently used. So though in this switchboard corpus, which is a very popularly used data set, is having 42 different tags, but all these tags are not equally likely. So they do not have the equal presence in the data set. So we have instead of that, we have used some most frequently used tags. The motivation is that as the SWBD DMA Basel tax set has fine-grained categories, not very useful for restricted domain applications. So we have proposed a new possible taxonomy that can divide the utterances into more generic classes. So basically now we are having only 5 classes: question, acknowledgement, greeting general, statement, and the comment. So only these 5 categories we have used as a part of the basically as a for developing the our classification module. So this is the in the description of our classes. So there is a question class contains utterances that represents any type of question. Like who is Chris Manning? This is a type of a question. Then greeting general is basically involves greetings, goodbyes, and small basic talks showing expression of gratitude towards the listener. Like good morning, good evening, how are you? So these are the different basically greetings. Then acknowledgement or CAT, this involves explicit affirmations, disagreement or confusion from the user side, as well as the instances that indicates end of the conversations. Like yeah, okay. So these are the kind of acknowledgement or the CAT. Then there is a comment. This involves asking the system to perform an action which may include display, search, and generate. So you are giving a comment. So like pass the book, open the door. So these are the different comment types utterances. Then there is a statement of the information, utterances that contain any piece of information that can be used to extract the attributes. Like he is in Austria right now. She is in Delhi. So this is a good book. So these are called the statements. So like here you can see the example of a dialogue. Agent is saying, hello, how may I help you? So this is a greeting. Then user is saying, show me flights to Mumbai today. So this is a comment. It is asking for showing the flights. Agent is saying, may I know the departure place? So this is a question. User is saying, oh, it's Bengaluru. So this is a statement. Agent is saying, oh, you want to fly from Bangalore to Mumbai. So this is a question. User is saying yes. So it is an acknowledgement. Agent is saying the flights are GS 383 at 2 p.m. and IN 541 and 10:30 p.m. So this is a statement. Then user is saying thank you for your information. So this is again a greeting. So this way you can see each of the utterances can be tagged with any of these 5 categories. Now this is our overall architecture. So there is a data pre-processing. So taxonomy you have already prepared. So we have used this 5 tags, fine-grained 5 tags, coarse-grained 5 tags. Initially there were 42 tags, but now we have simply used the 5 most frequently used tags. So basically we have annotated the data. Basically we have mapped these 42 tags into these 5 tags. So some tags are basically merged together. So that way annotation is basically performed. So then we have extracted all features. So several features are extracted. So all these features are given to the CRA conditional random field, and then there is a Dialog Act classifier. Okay. So basically all the features are given to the conditional random field, which is used as a classifier, and then we are generating the Dialog Acts. There is another possibility is that we can only select the best features. So no need to use all the features. You know the feature selection, there are several feature selection algorithms by applying which we can select carefully a subset of features. And then those features can be given to the CRF module for generating the dialog acts. So this is the methodology 2. And then there is another methodology where we are using the word vectors. So basically from the utterances, we have extracted the words, unique words, and we can get the corresponding representations of the words. So these word vectors are semantic representations of words in a semantic space. So there is a deep learning based package which is called the word2vec. So this word2vec, you can consider this as a black box. So this will take some words as input and it will show you the vector representation of the words. And the vectors are in the semantic space. So what does it mean? That the vector representations of the boy and girl would be very similar. Vector representation of the boy is very similar to vector representation of man. And vector representation of girl is very similar to vector representation of woman. So it is able to capture the semantic space as well. So then once we get the word vectors, we can apply some clustering technique. So like K-means algorithm, you know, K-means is a very popular clustering technique. So this K-means algorithm can be applied to group the sentences. Okay. So maybe as I mentioned that like woman, girl, ladies. So these words are having some kind of similar meaning. So these words can be grouped together. And this cluster can be represented by a cluster ID. So then the whole utterance can be represented. A utterance is basically a collection of words. So in the place of a particular word, we can use the cluster ID to represent the particular sentence. And then that sentence can be given as an input to the conditional random field and it will predict the dialog acts. So this is the methodology 3. So we have developed 3 different models for solving this dialog act classification task. So in the methodology 1, we have used the conditional random field. So this conditional random field is a classification model. So it is used for the sequential labeling task. So why it is called the sequential label task? Because the future output depends on the previous output. So like you can see that if it is question, then maybe we can assume that the next utterance would be statement. Okay. So this way basically it is called a sequential labeling task. The output of the current utterance depends on the output of the previous utterances. Then, so basically we have used several features like the lemma form of the word, lemma bigrams, part of speech tags and their bigrams. So we have used the lemma form of the words. So lemma form of the words means only the, you know, basically the code word. So, you know that basically the subscripts and the prefixes are removed and then we are using only the root word of a particular word. And root and lemma bigrams also consecutive to words and their lemmas are also considered. We have also used the part of speech tags and their bigrams. Then the speaker information, who is basically uttering, who is basically the speaker of the particular utterance. And then there are some class specific features which are used to improve the performance of the target class. So class specific features are, for example, for the question class, we are having the presence of the 5 age words. So whether the particular utterance has started with what, where, when, which, who, how, or question mark. So we have to see whether the particular sentence or the particular utterance has started with these WH words. Or greeting general, presence of sorry, thank you, hello, hi, etc. Or there is a scat, presence of who, okay, yes, no, why, etc. So these are the some class specific features. We are simply checking whether certain words are present in the feature list or not. So for the question category, these features are important. These 5 WH words, like whether there is a what, where, when, which, who, how, and question mark. Then there is a greeting general, presence of sorry, thank you, hello, hi, etc. And the cat, presence of hua, okay, yes, no, etc. So all these features are used, and then we have used the conditional random field to classify that particular whether the particular utterance, what is the dialog act of a particular utterance. So we have done an ablation study to improve the accuracy and identify important and contributing features. Because there are many features, maybe all the features are not important. We performed a thorough ablation study to identify the important features. conducted in the forward direction, it is the features are combined one after the other. The difference in the accuracies is used as an estimate of the importance of the feature. Okay. So the difference in the accuracies is used as an estimate of the importance of the feature. The base performing features are taken and rest of the features dropped to reduce the complexity. Okay. So base performing features are taken and rest of the features are dropped to reduce the complexity. So basically we have added, yeah, any question? So we have added the features one by one and then we have performed this ablation study. So the difference in the accuracies is used as an estimate of the importance of the feature. The base performance features are taken and rest of the features dropped to reduce the complexity. So in the methodology 2, as I mentioned, here we are using the conditional random field only as the classification algorithm. But now we have used the word embeddings. So basically we are taking the vector representations of the words and those are basically the embeddings of the words and these embeddings are used for the classification. So basically now we are not using any feature extraction, like these features, manually extracted features are not used. Rather, in a utterance there are multiple words. So all these words are basically converted into their vector representations by what to vec, or there are several vector representation tools available. So there is this BART or the globe. So these are all deep learning based tools and these deep learning based tools are basically taking the word as an input and then they are generating the vector representation of the words. So what we have to take the concept of the word embeddings of the corresponding words and then base performing features obtained from the ablation study. So there is a pretend Google News word embeddings of dimension 300 is basically used. So this is the methodology 2, that we have used the word embeddings of the corresponding words, base performing features obtained from the ablation study. So we have used the Google News word embedding, which is a deep learning based tool, and you give the word as an input and you will get the embedding representation of the word, which is of dimension 300. And this embedding basically captures the semantic meaning of the word. And then those are used as a feature for basically the CRF-based model. In the methodology 3, as I mentioned, that we have used a clustering based approach. So after generating the embeddings, we have applied a clustering based approach to group the words into different categories. So the words which are having the similar meaning are grouped into different categories. So word cluster IDs of the corresponding words are used and base performing features obtained from the ablation study, lemma unigram, lemma bigram, part of speech unigram, part of speech bigram. So basically we are using these features. We are using the word cluster IDs of the corresponding words. And apart from that, there are some other base performing features like the lemma unigram, lemma bigram, part of speech unigram, and the part of speech bigram. So this is the representation. So you can see, show me flights from Denver to Baltimore. So these are the individual words, show me flights, Baltimore, Denver, etc. So we are getting the vector representations of the individual words. So of dimension 300. So this is the representation of the word show. This is the representation of the word me. So this way you are having the vector representations of almost all the words. Then we are applying the clustering, K-means clustering technique, and we are grouping the similar words into different clusters. Like all the location names are grouped into single cluster. Baltimore, Denver, Newark, all are grouped into one cluster. Then me, her, you, him, all the pronouns are grouped into one cluster. Then from, to, in, people, all are grouped into one cluster. So this way basically we are clustering, applying clustering, and now each word is basically represented by the cluster ID, like G_3. So show is basically represented, is present in the cluster ID 3. Me is present in the cluster ID 29. So each word is basically represented by the cluster ID. So this way basically we are representing the particular utterance. So in the methodology 4, it is a deep learning based model. So here we have used the convolution neural network. Convolutional neural networks are very effective for computer vision field, but nowadays these are popularly used for solving different natural language processing technique problems as well. because these convolutional neural networks are capable of extracting some character level features. So basically for extracting some character level features, CNN are very useful. So we have used the CNN with fixed filter size of 3. And also CNN with multiple filters of size 3, 4, and 5. So basically, you know that CNN is used to extract some character level features, and then those features are used for the classification purpose. So to the baseline, variants of RNN such as LSTM are also incorporated. Finally, features such as part of speech and cluster IDs were augmented with the system. So this is the overall architecture. So we have the sentences, we have the word embeddings, and we also have the part of speech or the cluster embeddings. Then there is this convolutional layer. We have 3 into 3 layer, 4 into 4 layer, 5 into 5 layer. So then we are concatenating all the features, and then we are extracting some features using the convolutional layer 3 by 3, convolutional layer 4 by 4, convolutional layer 5 by 5. Then we are concatenating them all together, and we are getting a single feature representation for the input sentence, and then that is basically passed through the RNN unit, and then basically there is a dense layer which is predicting the correct dialog act. So this is the overall architecture of the model. So these are some results. So with the all features, when we are using the all features using the CRF as the classification module, when we are applying on the switchboard corpus, we are getting 72.50 accuracy. But with our proposed tag set of 5 tags, we are getting 90.87 accuracy. Now, similarly, with the all features, with the basically, you know that with the SWBD tag set, we are getting this 72.50% accuracy. But when we are doing the feature selection, then we are getting a 72.48% accuracy. But in case of our proposed tag set, there is an increase with the feature selection. So now methodology 2, where we have used the word embeddings only. So in the case, if you are using all the word embeddings and the CRF as the classification layer, then we are getting the accuracy of 69.28. And then for the proposed tag set, we are getting 88.96. And word embedding plus the base features with the switchboard corpus, we are getting the accuracy values of 72.94. And with the proposed tag set, we are getting the accuracy of 90.95. So now with this methodology 3, where we are using the clustering based approach. With the clustering based approach, with only the cluster IDs, if we are using with the switchboard original 42 tag set, we are getting 54.90. But with our 5 tag set, we are getting 84.04. But when you are adding this cluster IDs with the base features, then there is a improve in the accuracy. We are getting 72.89, and with the proposed 5 tag set, we are getting 90.87. So there is a huge improvement. So with the deep learning based models, we are getting, you can see with the multi-channel CNN plus the BiLSTM, we are getting the accuracy patterns. With the pattern speech features, we are getting 90.26. With the cluster based features, we are getting 91.13. So these are some error analysis. Like you can see, can you tell me the way to Patna? So here actual is basically it is a question, but our system is predicting as a command, because can you have two literal meaning. So can be a question, or can be a command as well. I am going to Lucknow, book me a hotel there. So here originally is a command, but our system is predicting as a information. So utterances are not explicitly command types. Then okay, I will also come tomorrow morning. So here original is information, but we are getting cat. Cat has much occurrence of words like okay, yeah, etc. And then no, it's not possible. So here the original is cat, but we are getting this as an information because it is a replying to a question. So in our next work, we have shown that instead of only relying on the utterances, like you have the textual description of the utterance. So instead of only relying on the textual description of the utterance, if we consider the user facial expressions or the audio tones, then maybe we will be able to detect the dialogue acts more efficiently. So basically, communicative intention can be expressed by you can be easily understood by the facial expressions, the audio tones, the eye movements, etc. So like okay, sure. So these are having several meanings. This okay, sure can be agreement or can be a disagreement. Maybe we can mention this as in a sarcastic way, or it could be a genuine agreement. So that can be only understood if you are only seeing the facial expressions or the audio tones. By seeing only the text information, it is very difficult to identify the sarcastic tones. So basically, in this particular work, we have used this multimodal information. This is called the multimodal processing. So multimodality is nowadays very popular because human beings, whenever we have to take a decision, we used to see the object, we used to touch the object, we used to hear the smell, and then basically we used to take a decision. So we have multiple sensors, and through these multiple sensors, we used to gather information in a multimodal setting. So basically, this multimodal features, multimodal information processing is nowadays very popular because we are often taking information from multiple sources, and then only you are taking a decision. So in case of Dialog Act also, this multimodality is very, very heavily used. So if you see the literature, most of the works in the DSC limit themselves to the utilizing only the textual modality. So there are very few works where the non-verbal features like the change of tone, facial expressions are basically used to identify the dialogue acts. So basically, thus stressing the role of incorporating multimodal inputs into the task. So basically, our task is to incorporate this multimodal information into the Dialog Act classification. So like utterances such as okay, sure, yeah, right can be considered as agreement or the disagreement. So either okay, sure can be, we can say in a agreement way or in a disagreement way. So, and also there is important information, the emotional state of the speaker has a substantial effect on the pragmatic content. So basically you can see that the emotional state of the speaker has a substantial effect on the pragmatic content. So mostly in expressive DAs such as greeting, thanking, apologizing, etc., speaker's emotion can assist in recognizing the communicative intention. So you know that if you can easily understand the emotional state of the user, you can also understand the communicative intention. So like okay, sure, and if the user is angry, then you can say that this okay, sure is a kind of disagreement only. But if the user is sad and he or she is saying okay, sure, then that is a kind of a agreement. Okay, so the emotional state of the user has a substantial effect on the pragmatic content. So inspired by this, we have basically developed a multitask based approach. We have proposed an attention based multitask framework where we have solved two tasks simultaneously, Dialog Act Classification and the emotion recognition. So Dialog Act Classification is our primary task and the emotion recognition is our auxiliary task. So with the help of the emotion recognition task, we are basically trying to improve the accuracy of the Dialog Act Classification. So we have proposed a attention-based multitask, multimodal deep neural network approach for jointly optimizing the DSC and the emotion recognition task. So here we have used the deep learning-based framework as again. So the data will be collected from different modalities. Like we have the video signals, we have the audio signals, and we have the text information. So data will be collected from all the three modalities. Then features will be extracted from all the three modalities. And finally, we have to combine these features to decide what is the Dialog Act. So basically here the emotional state information of the user will also be used to determine the Dialog Act. So the user emotional recognition is basically used as an auxiliary task. So we have created a new dataset which is called the EmoTIDA. This is called the multimodal emotional DA with high quality annotations of DAs, including emotionally aided cues for facilitating research in multimodal DSC and lead to a novel subtask, emotion aware DSC. So the dataset is called the EmoTIDA with high quality annotations of DAs, including emotionally aided cues for facilitating research in multimodal DSC and lead to a novel subtask, emotion aware DSC. So established that multitasking and multimodality boosted the identification of DAs compared to its single task and unimodal DSC variants. So basically that is the advantage that we have shown experimentally, that when you are considering information collected from multiple sensors, then there is a huge performance improvement compared to only text. So this is our data set that we have collected, Emotida. So first we have to basically, our aim was to develop a multimodal data set for the Dialog Act Classification. So I have scanned the literature for existing multimodal emotion recognition data set. We zeroed down to this IMOCAP and the mail data sets. So these two data sets are multimodal emotion detection data sets. So here there are multimodal information like the audios, videos, and text. And then there are having different dialogue acts. So there are having different emotion categories. So these data sets are not annotated for their corresponding dialogue acts. So SWPT DAMSL tag set comprises of 42 DA categories used as a basis for conceptualizing tag set for the Emotida data set. So 12 most commonly occurring tags were used to annotate utterances of the Emotida data set. So these 12 mostly chosen tags are greeting, question, answer, statement opinion, statement non-opinion, apology, comment, agreement, disagreement, acknowledgement, back channel, and the others. Okay. So basically these two data sets were annotated with the emotion categories, but they are not annotated with the Dialog Act categories. So we have manually annotated these data sets with the Dialog Act categories. And both these data sets are having three modalities: text, video, and audio. So after seeing the audio, video, and text only, we are giving it a particular tag as for the Dialog Act classification. So remove the discrepancy in the number of emotion tags for IMOCAP and mail dataset. The joy tag of the mail dataset was mapped to happy tag of the IMOCAP to finally settle on 10 emotional tags from the IMOCAP for the Emotida dataset. Conversations from IMOCAP and mail dataset were annotated for its corresponding DA tags. So this is the thing, our Emotida dataset is having total 1,341 dyadic and multiparty conversations, resulting in a total of 19,000 utterances. And each of these utterances is having the audios, videos, and a text. And these are some examples, like, speaker, the M4 is saying, adders don't snap, they sting. So this is a dialogue, it is a disagreement, and emotion is anger. Then Rachel is saying, well, I just checked our messages and Josia did not call. So this is a statement, and here emotion is basically sad. Then that's very amusing indeed. So here it is also a disagreement, but the emotion is angry. Come on, pick up, pick up. This is a kind of a comment, and the emotion is basically fear. So basically you can see in our dataset Emotida, IMOCAP is contributing 48% and mail is contributing 52%. And this is a speaker distribution. There are many speakers, and what is the percentage of data distribution in our dataset. So these are the distribution of the emotional levels. So you can see fear is very less present. There are less frequently used emotion tag. Disgust also. So most frequently used emotion tag is basically happy. So frustrated is only present in the IMOCAP. And then these are the distributions of different emotion levels in these two data sets. So happy is having most instances in both the data sets. Then followed by anger and the sadness. And frustrated is only present in the IMOCAP dataset, is not present in the mail dataset. Then there is this distribution of the DA labels. So as we have mentioned that we have total 12 DA labels: statement, question, answer, greeting, apology, so comment, etc. So this is the distribution. So you can see that statement is very much common. Opinion is very much common. So answer is very much common. So this shows the distribution of DA labels. So if we see the qualitative aspect of the Emotida, so the emotion basically helps us in understanding the proper Dialog Act. So these examples illustrate the importance of having emotional information while deciding the DA of an utterance. Like, I can't leave it. You caused a hole in my dinghy floor. Here the emotion is basically anger. And here, from the anger only, we can easily understand this is a kind of a disagreement. Now, well, I appreciate you coming over and talking to me. I mean, it definitely helps. So this is a kind of a sad. Here, the emotion is sad, and we can understand this is a kind of a acknowledgement. So the presence of emotion in the dataset caters the models with the ability to use additional information while reasoning about the DA. So these are some qualitative aspects of the emotida. Like you can see that if the utterance is fine, then you tell Roger because he was really looking forward to this. So text sometimes somehow suggests some agreement of the opinion. But if you listen to the audio, it is a commanding tone, and the video is basically furious. So from this, we can easily understand that this is not an agreement; this is a disagreement. Then that's very amusing indeed. So here also text implies agreement, but audio is a sarcastic tone and the video is a slight anger. So here we can easily understand this is not an agreement, this is a disagreement. So in both the examples, you can see the different sensors are giving us the complementary information. So there exists inconsistency between modalities, which acts as a strong indicator that multimodal information is also important in providing additional cues for identifying DAs. The ability of complementary information across multiple modalities improves the model's ability to learn discriminatory patterns that are responsible for this complex process. Okay, so the availability of the complementary information across multiple modalities improves the model's ability to learn discriminatory patterns that are responsible for this complex process. So this is then we have proposed a deep learning based architecture for handling this multimodal data. So as I mentioned, there are three modalities: audio, video, and text. So for the textual modality, we have used the word embedding techniques. As I mentioned, there are these word-to-vec models or the globe embedding or the BART embedding. So all these embeddings basically take text as an input or the word as an input, and they basically give us the vector representation of the word. So here in this particular work, we have used a globe embedding of dimension 300 to obtain representation of the words. Word embeddings of each word are concatenated to obtain a final utterance representation. Then there is this audio features. To elicit features from the audio, OpenSmile and open source software has been used. Features are concatenated together to form a 256 dimensional representation of each window. The final audio representation of each utterance is obtained by concatenating the feature vector for every window. Okay, so we have to consider the window by window. So we have to consider a window and then we have to extract all the audio features from the particular window. So features are concatenated together to form a 256 dimensional representation for each window. And to extract the important features from a window of audio signals, we are using the OpenSmile, which is open source software. The final audio representation of each utterance is obtained by concatenating the feature vector for every window. Then there are some video features. So basically, again, we have to consider the frame by frame. So videos are nothing but the collection of frames. So we have considered the important frames from a particular video, and then we have used a pool layer of an ImageNet, written ResNet 152 image classification module to extract the feature vector. The visual representation of each utterance is obtained by concatenating the 4096 dimensional vector for every frame. So now for the textual modality, we have used the three BiLSTMs. So one BiLSTM basically learns the Dialog Act Classification features tuned in accordance with the emotion features. Second BiLSTM is used to learn the emotion recognition features regulated by the learning of the DA features. And third BiLSTM learns private features for the task of DAC not influenced by emotions. And then there are some audio features and the video features are passed through some multi-layer perceptrons, fully connected layers to extract some features. We have used three attention layers: self-attention, intermodal attention, inter-task attention. In order to basically focus on some portion of the text, we have used the self-attention. Intermodal attention basically somehow aligns the information present in the multiple modalities. And as there are two tasks, so this inter-task attention is basically helps in understanding the two tasks well. So we are doing this fusion of the attentions. So there are 13 different attention outputs for different tasks and modalities are computed from its corresponding attention scores. And then we have used this concatenation to get the vector representations of one for the Dialog Act, one for the emotion recognition. So these are the visual concatenation operations. So we are concatenating the different feature vectors, and then we are getting a sentence representation for the Dialog Act and one sentence representation for the emotion recognition. So then basically you can see there is this classification layer, and we are basically passing through the classification layer. So there are two tasks, Dialog Act and the emotion. So there are two separate classification layers. So but they are taking the same feature, and then they are doing the classification of the task. So sentence representation of each of the tasks from the TAs are connected to a fully connected layer, which in turn consists of output neurons for both the tasks. The errors computed from each of these channels are backpropagated jointly to successive prior layers, and the model to learn joint features of both the tasks. So there will be some error from the Dialog Act classification. There will be some errors from the emotion detection. So we'll sum up the errors, and then those errors will be backpropagated to train the entire system. So we have basically taken the results in different settings. So we have, this IMOCAP emoter is basically having two data sets, IMOCAP and the mail. So basically we have taken the results in the dyadic setting and also multiparty setting and all together. So there are two tasks, Dialog Act Classification and the emotion recognition. So in the modality wise, we performed the ablation study. Either we are considering only the text, audio, or the video modalities, or we are considering two modalities together, text plus audio, audio plus video, text plus video, or text plus audio plus video, all three together. So these are the ablation study of the modalities. So only with the text modality, what is the performance? Only with the audio modality, what is the performance? Only with the video modality, what is the performance? So you can see the text modality only basically helps a lot. So text modality is basically gaining the accuracy of F1 score of 50%, whereas the audio and the videos are in the range of 20s. Then text plus audio together is giving us a better result compared to text. Audio plus video doesn't perform good. Text plus video also again performs the best, 57.96. So basically, we also did a basically ablation study. So, and there is another approach. So instead of doing this multitasking, so here, as you know, that we have solved both the tasks together, Dialog Act Classification and the emotion recognition. So, but instead of doing these two together, instead of doing that together, we can also use the emotional features for helping in the Dialog Act Classification. So this is our last row. So where the emotional features are used for Dialog Act Classification. So these are some results, like she is not Larry's girl. So here the true level is disagreement. The single task is saying is a statement, but the multitask is saying is a disagreement. Similarly, I know it was amazing. I mean to totally nailed it. It was beautiful. So again, this is an agreement. Multitask is also giving us the agreement, or the single task was giving others. So basically, you can see that multitasking, when we are analyzing the emotional state of the user, so that basically helps us in understanding the correct Dialog Act. So in almost all cases, you can see, except this one, probably 100 people told her she is foolish, but she is weighted. So it is a true level is others, but the multitask is giving as a statement, and single task is wrongly predicted as a question. And these are some further ablation study of our proposed model. So as I mentioned, there are three different attention: self-attention, inter-task attention, intermodal attention. So we have performed experiments with all these different attentions. So what is happening with, because our text plus video, from this table you can understand that text plus video is giving us the best F measure score or best the accuracy. Audio is not helping in this case. When we are adding audio into this, there is a decrease in the performance. So that's why all these ablation studies are performed with the help of the text plus the video modality. So when we are applying the self attention or the intermodal attention or the task attention, you can see there is a decrease in the F1 score and the accuracy. So when we are combining, when we are using all the three attentions, then only we are getting the highest F1 score and the highest accuracy. And this is our best model, which is giving 60.88 accuracy and 57.96% F1 score. And also we have done some early fusion, late fusion, and the hypothesis level fusion. So again, you can see that our deep learning based model outperforms them. So this is a visualization of the learned weights for a sample utterance. So you can see that initially when we are solving the DSE, our focus on the ESCS part. But if you are solving this in a multitask setting, then the focus is on the can't word or the me word. So now, as I mentioned, this dialogue natural language understanding module is having two other components. One is called the intent classification detection and the other is called the slot filling. So as I mentioned, that intent detection is basically to understand the intention of the user. So whether the user wants to book a flight or he is simply querying about a flight or he is asking about the restaurant or maybe he is interested in booking a restaurant. So these are some examples of the intents. So intent detection and slot filling are the task of interpreting user comments or queries by extracting the intent and the relevant slots. Intent detection is framed as a classification task that maps an observation sequence to a particular label Y, that is to acquire the most probable intent label given some word sequence. And slot filling is often framed as a sequence labeling task. So basically here you can see the slots are the first class. So there is a B class type, class is a I class type. Then Boston is a B from location, Denver is a 2 from location. So this way basically slot means to identify the information present in a particular utterance. So this is a sequence labeling task which maps an observation sequence into a sequence of labels Y, that is to acquire the most probable slot sequence given some word sequence. And here the intention is the airfare. First class fares from Boston to London. So the intention is basically the airfare. So we have used these three data sets, ATIS, NIPS, and the MIT restaurant movie corpus. So ATIS contains user utterances related to the air travel information system. SNPs contains several day-to-day life user comment categories like play, song, book a restaurant, etc. And then MIT restaurant movie corpus, it contains user utterances related to movies and the restaurant domains. So these are the three popularly used data sets, and these we have used for the intent and the slot modeling. So again, we have used some deep learning based models for solving this intent detection and the slot filling module. So we have used the LSTM GRU CRF network. So this particular approach combines a LSTM GRU network with CRF network to obtain a LSTM GRU CRF model. The idea behind such an approach is that the network can then efficiently utilize the past input features because of the presence of the LSTM layer, followed by a CRF layer, which can then add sentence level tag information. CRF layer predicts the current tag with the help of past and future tags, which is quite similar to a bidirectional LSTM or GRU network that makes use of past and future data inputs. So then we have also a bi-LSTM, like bi-LSTMs are more advanced version of LSTM. LSTM can only see the previous input, all the previous to context, but the bi-LSTM can see previous and the next words as well. So we have used the bi-LSTM GRU CRF network. The model combines a bidirectional LSTM GRU network with CRF model to obtain a bi-LSTM GRU CRF model, along with the past input features and sentence level tag information as used in a LSTM GRU CRF model. The model utilizes the future input features as well. So this is the thing that here this is the LSTM model. So show flights from Tacoma to Nass Valley. So here there is this forward. So it will basically there is a basically this is LSTM. So the long short-term memory network. So it basically can see the previous utterance as well. And then there is a state representation. And then there is this BIOS stream. So BIOS stream is able to, there is a forward pass, there is a backward pass. So the inputs, the basically utterance can see the previous, the current utterance can see the previous utterance and also the next utterances. So this is a BIOS stream GRU CRF model. And we have taken results of different models. So you can see that when you are using the BIOS stream CRF model, that gives us the best result. So accuracy wise, we are getting 98.15%, and the F1 score wise, we are getting 97.94%. So that was the intent and the slot module. So now, as I mentioned, the dialog systems is having several components. So one is the natural language understanding. So in the natural language understanding module, we have discussed about the Dialog Act Classification, interdetection, and the slot filling. So you can see that Dialog Act Classification is basically to identify the communicative intention of a speaker, and it is a classification problem. So basically, there are some classes, and given the utterance, we have to somehow identify the correct class. And then there is this intent. Intent is basically to understand what the user trying to do, whether user wants to book a restaurant or wants to book a hotel, or he is simply asking about the price. So these are called the intents. And the slots are the important information present in the utterance. So now there is this dialog manager strategy. So dialog manager strategy takes input from the natural language understanding module. So natural language understanding module has already extracted information in the form of slots, and then those slots are basically given to the dialog manager to basically to map the state into action. So the state is nothing but the slot values and also the type of the dialog. And this state will be mapped to basically this state will be mapped to an action by the use of this dialog manager component. So the main function of the dialog management component is to control the flow of the dialog. This involves the following tasks: determining whether sufficient information has been elicited from the user in order to take a suitable action. So basically, we have to somehow understand whether sufficient information has been given, has been taken from the user in order to take a suitable action. And then we have to execute an action. So communicate with an application or communicate with the user. So this is a reinforcement learning based agent. So you can see the RL allows the machines or software agent to learn its ideal behavior based on the feedback from the environment. So reinforcement learning basically takes the agent as an input. So basically the output from the natural language understanding module is given as an input to the agent module. And then the agent module is basically so basically agent module basically takes an action. So this action will be translated into some text by using the environment. So basically environment basically gives us the reward or the penalty. So agent is picking up an action. So if the action is correct, then there will be a reward. Otherwise, there will be a penalty. So the RL is a software agent which is responsible for mapping the state into action. So it is inside the agent. So agent, based on the input, it will predict an action, and this action, whether it is correct or not, that will be checked from the environment. So that environment will give some reward or the penalty. The underlying principle behind RL, law of effect: you do something, something good happens. So you try to do it more often if a similar situation arises. You do something, something bad happens. So you try to do it less often in a similar situation arises. So why RL? So currently the dialog management strategy involved employer is completely rule-based. So you know that rule-based means that you extract some rules and then they basically manually use that. So if this is so basically there will be a state to action mapping. Here the inclusion of RL minimizes the use of handcrafting, data-driven, to exploit the recent advances in reinforcement learning and the deep learning, end-to-end synthesis, and it basically creates an infrastructure that will be used across different domains. So this is our RL chatbot basically. So there is a user is saying something. So there is a speech to text converted module. So this speech to text converted module is basically translating the user speech into the text format. Then this text format is given to the chatbot. So chatbot is having the NLU module and the DM module and the NLG module. So the NLU module will extract the relevant information from the utterance, and then those information could be given to the dialog manager. Now dialog manager will pick up the correct action. So then there is this text to speech module. So this text to speech module will convert the action into the will basically convert the action, and then there will be a reward or the penalty. So user will give the reward or the penalty. So this will basically it will work. So reinforcement learning, any RL setup is mathematically described in terms of abstraction called the Markov decision process. So here Markov decision process is having some tuples. S is the finite state space, A is the finite action space, R is the reward model, P is the transition model, and rho is the initial state distribution. Okay, so this MDP is described by this. S is the finite state space, A is the set of actions, R is the reward model, P is the transition model, and rho is the initial state distribution. So the idea is to implement RL for learning dialogue strategies using the Q learning algorithm. Okay. So there is a Q learning algorithm. So this Q function is basically a kind of quality function. It takes the state information as an input, and then it basically checks the quality of the state. So yeah, given an action, the state will be moved to a new state. So what is the quality of the new state? That is basically checked by the Q function. So the main idea in Q learning is that we can iteratively approximate the Q function using the Bellman equation while dynamic programming, but still slow. Hence the Q function will be approximated using a neural network. So in this case, basically you can see that Q function is a basically a kind of a function which basically checks the quality of a particular state. So the Q function will be approximated using a neural network. So this Q function can be approximated by a neural network. So what is the Q learning? Q learning defines a function Q of SA, which represents the discounted future reward when we perform action A in state S and continue optimally from that particular point. So it is a discounted future reward. So if you are in state S and if you are picking the action A, then what will happen? So what will be the reward or the penalty for that? So this is an estimate of the same. So the way to think about Q of SA is that it is the best possible score at the end of an episode after performing action A in state S. It is called Q function because it represents the quality of certain action in given state. Okay, so it represents the quality of certain action in given state. If we want to select the action that results in the highest Q value, then basically we have to select the particular action. So given a particular state, you have to see which action gives us the highest Q value, and accordingly the particular action will be picked up. So basically you can see that this is the double deep Q network. So in our approach, we have used a hierarchical approach for efficient multi-intent dialogue policy learning. So here where we are saying that multi-intent, so there are some utterances like you see that I would like to, like this one, show me flights and cheapest fares from Pittsburgh to Denver. So here the user is basically not only asking for the flight tickets, he or she is asking for the flights, but also the cheapest fare. So here there are multiple intents which are flight and the airfare. Okay, show me flights and the cheapest fares from Pittsburgh to Denver. So here there are multiple intents which are flight and the airfare. So how to handle this kind of utterances? So if the user is asking multiple questions in a single utterance, then it is called the multi-intent dialogues. So intent captures the main communicative intention of the user utterances. The multi-intent captures more than one intention present in the user utterance. So we have developed a hierarchical dialog manager because there are multiple intents. So if there are multiple intents, then the agent will be confused. Which intent to be served first? So that's why you have to use a hierarchical platform. So there will be intent module. So intent module will select a particular intent to be served, And then there will be a there will be a policy, basically there will be a sub-module which will be responsible for performing the particular intent. And these are all deep neural networks. So for solving a particular intent, there is a separate neural network. So if there are two intents, flight and the airfare, so there are two different neural network. One is for the flight intent, another is for the airfare intent. So basically, we have to manage the multi-intent conversations. So they have to develop a hierarchical dialogue management strategy for task-oriented virtual agent. So you will be using the reinforcement learning, so which is the deep reinforcement learning. This is the proposed strategy. So there is this multi-hot encoded intent state space. So that there are multiple dialogues, there are multiple neural networks. So each neural network is responsible for serving a particular intent. So if the user utterance is having multiple intents, then those will be encoded here in this multi-hot encoded intent space representation. And then there are multiple neural networks for serving multiple intents. And these are the global slot trackers. So each intent is having some slots. So those slot values are basically stored here. Like if you want to serve show me flights. So in that case, basically you need to know the source city, destination city, time of arrival, time of travel, date of travel, whether it is a business class or the economy class. So these are the important slots. So that those information are stored in the global slot tracker. So we have to select a particular intent from this DRL, selecting DRL model based on intent state space. You have to select a particular intent. Accordingly, a particular deep learning network will be invoked, because for individual intent, there are different individual intent networks. So a particular intent network will be invoked. And then there is a global slot tracker, like for the cheapest, for the show me flights and the cheapest fare. So basically here that there are two intents, flight and the fare. So for both the cases, maybe there are many common slots, like the source city, destination city, date, time. These are all common slots. So if some intents are sharing some common slots, then we will not ask user for the same slots multiple times. Rather, there is a global slot tracker or global state variable, so which is having information of all the slots. Okay, so that way basically we will be using. And then there is this slot filling on the NLG N2 module, to and from conversation of the VA and the user. End of intent moving to next intent. Suppose when the one intent is already served, it will move to the another intent. So basically, user utterance. This is an overall proposed approach. So there is a user utterance. There is an intent module. So this intent module will identify all the intents present in a user utterance, and then those will be encoded in the multi-hot embedding representation. And this is from here. At a time, only one intent will be invoked, and for each intent, we have a single deep neural network. And that deep neural network will be will basically serve the particular intent. It will be responsible for serving the particular intent. And this is a global slot tracker, because there are multiple intents may share some slot values. So the slot values remain same over the intents. So basically, this is the task that train a set of networks where each network represents serving a particular intent to complete a particular sub-dialog. Each deep neural network exhibits unique behavior while interacting with the user to complete its task optimally. Therefore, in a network of reinforcement learning agents, an action selection is performed based on an optimal policy network. So basically, we have to search for the optimal policy. So we have to select that particular action, which basically attains the maximum Q value. So this is used for the low-level hierarchy, that is using the DRL model transition. For intent I belongs to I, set of intents is determined by. So a particular intent will be selected. So and this is from the high-level hierarchy. And then once the intent is selected, that will be served by the low-level intent modules. So for the here our state space is having two. It is a pair of states S1, S2. So S1 is having n variables corresponding to the number of intents. So if there are n number of intents, then there will be n variables. So the presence of one represents that particular intent is present in the utterance, and the presence of zero indicates that the intent is not present in the utterance. And the S2 is basically the set of slots. For each of the intents, S2 is a tuple of variables of the length equal to the number of slots required to be filled up for the particular intent. So basically then there is this action space. So the action space consists of 21 unique actions categorized in 3 different classes: ask, reverse, or the salutation. This is a reward function. So there is a task-based reward. So each time we are seeing that this is a new state and this is a old state. So state is nothing but the slot values. So we have already seen the state is nothing but the confidence values of the slots. So from a user utterance, we are extracting the slots with some confidence values. So those confidence values of the slots are basically part of the state. So basically after at each step there will be a state representation. And now when there will be more number of conversations, there will be new state. So basically this is the new state, this is the current state. So after picking up an action, whether we are able to improve the state information or not. So that is the task of this reward. So current state is the current state, and after we were at state S. Now we are taking the action A, and we will move to state S dash. So this is the difference, that what is the difference between the new state and the current state. We are multiplying this with W1 minus W2. So NS state is the summation of the confidence scores of all state variables in the state vector S obtained after taking an action A in state S. CS state is the summation of confidence scores of all state variables in state vector S. W1 and W2 are some parameters or the parameters. We have said the W1 equal to 1 and W2 equal to 8. So W2 is introduced because if the agent will keep on taking the same action multiple times, then there is always a penalty. Okay, suppose the agent is always picking up the same action, then we need to insert some penalty. So this W2 is used just as a penalty. In case of termination conditions, so when suppose the agent has already solved all the tasks of the user, okay, and now suppose the agent is taking a termination action in order to terminate the conversation or the dialogue. In that case, you have to see whether the task is really successful or not. So task will be successful if all the slot values present in the state are having values greater than 0.7. So if the slot is having a sufficient confidence, then only we can say that the agent has successfully solved the particular task. So the condition is that how many slots has a confidence score with threshold say 0.7. The condition is satisfied when all slots match the criteria. So if the condition is not satisfied, then the reward is EV minus ES. So in this case, we are giving a very this is reward. Otherwise, if the condition is satisfied, then there is always encouragement. So the agent will be given some reward. So these are some results. So you can see that over the iterations, how the average reward is changing. So you see after some iterations, there is a convergence. So there is no change in the average reward. So this is also with the average reward of the iterations. And for the flat RL, like here we have used the hierarchical RL technique. So I have mentioned this architecture. So there are two RL modules. So one is at the intent level, other is at the policy level. So intent level, hierarchical intent level DRL is responsible for picking the current intent, and then there are some new deep at the RL modules for serving all the intents. So basically, what will happen if we don't do the hierarchical structure? If we do a flat RLL, so there will be multiple intents. So the intents will be served one by one. So in that case, it is called the flat RL. So then this is the behavior. So average reward versus the iterations. So these are some examples, like see the agent is saying, hello, how can I help you? User is saying, I would like to travel from Pittsburgh to Denver. The system log intent change to flight. Agent is asking, please specify the class of flight. User is saying, I want to travel in economy class. So agent is asking specify the time and date. So see, the agent is asking all related slots from the user. User is saying on 4th January at morning. Agent is asking the flights from Pittsburgh to Denver on 4th January at morning. My economic classes are this. So once it got all the slot values, like see, these are the required slots. So all the slot values are having values greater than 0.7. So now with these slot values, it can do a database search and then it can retrieve the answer. So the flights from Pittsburgh to Denver on 4th January at morning by economy classes are this. Do you need anything else? So user is saying, show me the cheapest fares. So system log intent changed to airfare. Okay. So now initially see the first intent was 1, all the other intents was 0. Now the second intent is 1. Okay, this is the S1 because in the first hierarchy we are having the intent information. And now but we are borrowing the same state from the previous state. So because it is a global state representation, so we are borrowing the information from the previous state. So agent is asking, so only there is one new slot, that is whether the user is asking for the round trip or the one fare. So agent is asking round trip or the one way fare. User is saying round trip. So basically then the corresponding slot is filled up. The chip then it is able to do the database search and it is giving the answer. The cheapest fare of the flight from Pittsburgh to Denver on 4th January and round trip via economy class is $1,000 for JW 456. Do you need anything else? Agent user is saying no thanks. So basically you can see that the agent is able to solve the user task with success. So we have also worked on the virtual agent in Hindi. So we intend to exploit the fact that even though there is a language difference, but the semantic relationship of a specific task coexists irrespective of any language barriers. Okay, so yes. So we have reused the, yes, any question?
No, ma'am, it's all right.
Yeah. So we have reused the same DM module, but we have replaced the NLU module because now you know that utterances are in Hindi. So you have to, the natural language understanding module has to understand the Hindi language, and then only it can identify the intent on the slots of the dialog acts. So the natural language understanding module, natural language generation module will be in Hindi language, but the dialog manager as such, there will be no change. Because for the dialog manager, it is taking the state as an input and it is the action is the output. So the state is basically coming from the output of the natural language understanding. So the natural language understanding only has to deal with the user utterance, and the user utterance is given in the Hindi language. So basically then NLU module has to understand the Hindi language and it will extract the information from the dialogue and from the utterance, and it will basically extract this information and those will be given to the user. So the IC intent and the slot module has been trained on the semantic tagging corpus developed in the Hindi for the ATIS dataset. Okay, so we have developed the Hindi ATIS is available in the English dataset. So we have somehow tagged this with the Hindi. We have translated this into the Hindi language, and then we have manually tagged this dataset for the intent and the slot. And following the similar approach, the DM module can be used for any other language for the related task, given that there is an availability of a semantic tagging corpus. So you understand that natural language understanding and the natural language generation module should be now modified to deal with the Hindi data, but there will be no change in the dialog manager because the dialog manager is taking only the state and giving us the action. It's like this is the thing, see that we are able to converse in Hindi as well. Okay, so this is the example how it is can be worked in the Hindi language. So I think now I have to stop. So if you have any question, please ask me. Yes, so there are some questions.
Yes, ma'am. Thank you for your wonderful talk. So, and your knowledge you imparted would definitely motivate and inspire the research community and the different faculty members of the country in the area of AI and machine learning. Now some questions actually from different participants is coming in the message box.
Yeah.
So ma'am, I go through this.
Yeah, or maybe I can also read. Like Saurabh Mandal has asked, learn, okay, so I have two specific questions. What to make low BART? Which one you find best for the datasets used for your dialog Act classification technique? Okay, so we have used the globe embedding, okay, but I think BART will give you the best result because BART or the GPT-2, these are the recent language models. So we have not tested with BART. We have used the globe embedding only. But my personal experience is that if you will be using the BART or the GPT-2, maybe you will get better accuracy or the better F1 score. But we have used in our particular task only the globe embedding. So do you think the dialog systems can be mixed with the multi-document text summarization where the answer given by the bot could be a description of something which summarized text in multiple lines? Yes, very much correct. So basically we can use the dialog systems for the multi-document text summarization. Yes, so maybe multi-document text summarization can be used to get a summary, and then maybe that summary can be given to the dialog system. So basically, we are working on this, like we are also working on the mental health. So for the mental health, that suppose a user has somebody suffering from the depression. So user is expressing his own problems. So in that case, the problems are there are multiple utterances. So the user is expressing his views by using multiple sentences. So it is not possible to encode all the utterances. Okay, so there we are basically using the summarization to get a summarized sentence, and then that sentence can be given as an input to the Dialog Act classification. So yes, Saurabh, we are. I think summarization is very much useful for Dialog Act. So if your utterances are very long, you are not able to encode the whole utterance. Maybe in that case, if it is too long, then the context will be lost. So in that case, you have to apply summarization. You just reduce the length of the utterance and then apply, then give it to the Dialog Act classifier. Yeah, Sanjeev Gupta, for clustering purpose, K-means utilized, why not? Yeah, any other clustering technique can also be used. K-means is very simple one. You know that K-means is very simple one. That's why basically we have used this K-means algorithm. But any other algorithm can be used because already our system is so heavy. It was a deep learning based approach. There was this what-to-vec model, CRF. So that's why just in order to make this simple, we have used the K-means. But yes, you can use any other clustering algorithms. Which software tool we have to use for this? So we have used the PyTorch. So these deep learning packages are available in PyTorch only or TensorFlow. So basically, mostly we are using this PyTorch to implement these tools. So already in the deep learning, several library functions are available in the PyTorch. Yeah, so Manisha, so as I mentioned in a part of my work that we are now working on the Hindi language. So if you want to work on the Hindi or any regional languages, then you have to have a good collection of data. Like this ATs, switchboard, these data sets are available in English. So maybe you can manually translate these data sets into regional languages. And then the natural language understanding modules can be developed on those regional languages. Okay, so you only need to have a big corpus for the regional languages, and then you can easily build your machine learning tools because there are many embedding techniques available. Like recently, Google India has developed this Moodle BART. So this Moodle BART is capable of giving embedding representations of different Indian language words available in different Indian languages. So like if you want to get the embedding representation of a Bengali word, so this Moodle BART is capable of doing that. So you can use the Moodle BART instead of the globe embedding or the BART embedding. You can use the Moodle BART to get the embedding representations of the words in the regional languages, and then you can build your own classification module for the natural language understanding.
Good evening, ma'am.
Yes.
One question we have got from the YouTube also. The question is from Pranesh. He said that which one is best for classification, either ML or DL?
So if you have enough data, then obviously deep learning is very much useful, because deep learning is capable of extracting some hidden features. Like if you want to use some machine learning models, then you need to manually identify some features. Like I have shown in our Dialog Act Classification model, we have identified the part of speech, lemma. These are the different features that we have used for Dialog Classification. That was a manual feature engineering. So you have to manually identify the important features, and then those features can be given to develop the machine learning model. But if suppose you have enough data, you don't want to spend time in manual feature engineering, then you should go for the deep learning. But deep learning is very much data hungry, so it requires enough data to extract the useful features. Okay, so that is basically these are two different techniques. So I would like to say that nowadays deep learning is people are mostly using the deep learning based techniques, because in that case you do not have to extract the features. So basically, if you have enough data, then you should explore using the deep learning techniques. Yeah.
Thank you, ma'am. And any other questions from any other participants? Okay, thank you. So now I request